Hello, everyone. Hope you brought your cup of coffee. You probably need it. It's a late evening and a lot of content. So I'm Lucian. I'm a staff engineer at Garmin. And today we're going to talk about concurrency hylomorphism. My last year talk, I started with this slide. While this still applies, I think a better first slide for this talk would be this one. This talk on concurrency is hard. And the reason I'm saying that is we're going to talk about a lot of things. We're going to talk about 3 programming languages, C++, Hylo, and the future version of Hylo. We're going to talk about matter and form. We're going to talk about theory, practice. We're going to talk about stackful coroutines, a little bit about stackless coroutines, and philosophy. And they all somehow tie together to concurrency. So yeah, it's going to be an interesting talk. So I bet you all came here to learn what hylomorphism is, right? This comes from Aristotle, and it's the theory that says that every physical object is compound of matter, hyle, and form, morphe, right? And he uses that theory to describe composition, how things compose in the physical world. He describes that the whole needs always to be bigger than the parts. He also says that matter is potentiality, so what thing can be built out of, and the form is the actuality, what the thing actually is. Interestingly enough, he sees the body and the soul as being forms of hyle and morphe. So it's a nice, interesting thing. There's also a term in computer science which represents a recursive function corresponding to the composition of anamorphism followed by a catamorphism. We're now going to talk about that. So what we're trying to do in this talk, much like trying to align the stars, is try to align hyle and morphe for concurrency. Right? Try to align the potentiality of concurrency with the actuality. Try to put them together so that it's becoming an easier thing for the user. Yeah. Also, what we are going to do is going to start from the theory and try to go to practice in a way that kind of leaves a small gap between those two, right? It should not be a huge gap between theory and practice and like, oh my God, how do we come up with so many concepts and so many things that we need to do and learn and do them right? A bit of warning, this whole talk is based on a prototype, or actually a series of prototypes, right? So don't take everything that you see here as a production code that you really need to go and put it into your production software, right? We're going to discuss the C++ library. It's out there, it's working, but it's not fully featured, and we are going to talk about some examples. So here is the agenda for today. You'll have a QR code here in which you can find some references and the slides, and we are going to talk about modeling concurrency, a Hylo programming language, expressing concurrency, what is structured concurrency. We're going to delve into implementation details, some early measurements, then a lot of analysis, and then finally some takeaways. So, lots of material. So let's get started. Hylo. So the Hylo programming language was formerly known as Val, was introduced at C++ now 2022 by a keynote by Dave Abrahams and Dimi Rakoldon. And it has 3 pillars. It's fast by definition, safe by default, and it's simple. And when I say safe by default, what I mean is it doesn't have any undefined behavior, but yet it's still fast and it still allows compilers to optimize the code. Now, I need to say this in public. So a little bit of the history of the name Hylo. So the Hylo Val team at that time got a cease and desist letter because the name was already taken and they had to stop using the name. So what they did, they asked the contributors to put up ideas, proposal, and then try to run them down, and they vote those things. And as part of those things that were considered was value semantic, whole part relationship, generic programming, and so on. And one of the key persons that influenced the language was Alex Stepanov. And moreover, this talk was actually highly influential to the whole development of the Hyle programming language. So let's try to hear what Alex has to say.
Sudden realization that, after all, Aristotle was right. Aristotle was always right.
One more time.
Sudden realization that, after all, Aristotle was right. Aristotle was always right.
Aristotle was always right. And he got that into the discussion of whole-part relationship, which, what I mentioned, was at the core of Hylo. And he also references Aristotelian processes during his talk. So we were there looking for inspiration names, and one of the things in Aristotle's terminology was Hylo. And then everybody said, like, yeah, that's a great name for a language. Let's have the language name Hylo. So that's how it came to be. So what is Hylo? It builds upon the best parts of C++ and try to ditch away the rest. More specifically, it builds on the idea of value semantics, and it kind of tries to make it better. In Hylo, everything is passed by value without any copy. Actually, all the copies and all the moves are explicit. There is no implicit copy and move. It has a consuming move semantics, and then it defines rules for capturing access without consuming. And with that kind of model, you can build an entire language that is safe and fast by definition and easy to use. So let's look at a small example. C++ first. So we have this append2 function that takes a destination vector and a value and tries to do a double pushback into that function, right? Looks a regular function. No surprises in there. But what happens if I'm calling this function with an element from the vector itself? Will it work? It won't, because the first pushback may actually destroy my element, right? That's a problem. And you can arguably say that the function does the right thing and the caller does the right thing. So somehow you need to have reasoning for the entire program to understand what's going on. In Hylo, if you're trying to do the same thing, that would fail. So where is my mouse? I can't find it. No matter. So the first append just says error. You can't have the same value, the same vector put both as mutable and as immutable. And what it does, it forces you to make a copy, right? You see here that copies and moves are explicit. I'm not going to talk about too much about syntax. It's heavily inspired by Swift, changes a few things here and there, but you're all programmers, you've seen code, you pretty much understand this. At the heart of this example is the law of exclusivity. That is, it doesn't allow you to have simultaneous read and write access for a variable. Also, you can't have write and write access. Everything that you can have is read and read access, right? Or, of course, you can have either one read or one write. And that restriction gives you a huge power because it allows local reasoning. There is no spooky action at a distance if you apply this rule, right? So if you look at a piece of function, you're certain, and the compiler guarantees, that there is nobody else in your code base that can change the output of anything that's in there. You have full reasoning capacity to consider that and reason about your function. And what we are trying to build here is a concurrency model that was originally targeting Hylo, but I've implemented in C++, so it's not just Hylo. But you need to have that kind of starting point of where it is. So modeling concurrency. This time I'm going to focus on the hyle, on the substance of things, and just look at the theory. So what is concurrency? Concurrency is the partial ordering of task execution. That's it. That's everything that we need to know about what concurrency is. Now, at execution, at runtime, there are three possibilities that you can arrange the code. If you have two distinct tasks, A and B, either A happens before B, either B happens before A, or they somehow happen concurrently. Neither of those two is true, right? There is no other possibility that you can have at runtime with two distinct work items. Graphically, you would put it something like that. Either A happens before B, either B happens before A, or somehow they happen concurrently. This is execution time. At design time, concurrency means expressing constraints about execution without actually considering all the execution parameters, at some point ignoring the actual execution. That means that I can have this example. These are just the simplest cases. I can have either A be the predecessor of B, B be the predecessor of A. I can have concurrent execution of A and B, or I can have mutual execution. Practically, there's not an interesting operation because each time you have to do those, either you do A before B or B before A, so you can solve it easily. But those are kind of the basic blocks. There are more constraints that you can represent in your program, but those are the first four. These, I try to put them here in more algebraic form. This is the advanced concurrent constraint. You may have conditional concurrency, like sometimes those two tasks are concurrent, sometimes they have to be mutually exclusive. And of course, you have system in which you have more than two work items, right? But those are kind of rare. Like if we manage the basic ones, then we can manage roughly everything. And that's it. That's everything that we need to know about concurrency. There's nothing more to concurrency. If we manage to put this into practice, into a simple form, it's done. We are done. So let's try to look at the form of this. And I'm going to walk you through some examples here from simple things to more complex. I'm going to use those three languages, C++, the current version of Hylo, and the potential future version of Hylo. So in C++, with my library, which as you can see by the namespace, it's called concur to full. What you can do is spawn a work item, you give it a lambda, that will execute somehow concurrently with some whatever else you're doing in there. And that returns a future, and then at some point you await the future, right? You close the loop. In Hylo, and that's the current version of Hylo, you can do the same thing. There is a spawn function that needs to be improved a little bit. Then you can do exactly the same thing, slightly different syntax. In the future version of Hylo, my hope is that we can clean that up a little bit and make it nice for the users. Right, so that's a starting example. That's the hello world for concurrency. It's pretty easy, right? It's not going to get much more complicated. This is an example with task relations. And you see here that I have everything. I have predecessor and successor relationship. I have concurrent execution. And I also have mutually exclusive because I have some orders in there, right? T1 cannot be executed at the same time at T5 because there is the dependency between them. How would you express this in the code? So using a future version of Hylo, you would just say T1, then T2 and T3 are running concurrently. You await, making sure that from now on the point, there's one single flow of execution. and then you have T4 or T5. My simple example, I'm just using prints to represent the tasks, right? So that's the basic pattern. It's really just it. There are a few complications, but this is roughly 80% of what we need to do. That allows us to build incredibly complex things. So this is a more complex graph, and this is the code running from. You see it from the back, right? The font size is good. Okay, I thought so. So you can look at it from a higher level perspective, and you see that it has T1 and it has T18, and then in my example, I'm using the same thing. Like again, I cannot find my mouse. Here it is. So I'm having run task of 1. That's my first task, and I have run task of 18, and then in between I have some other things. But you see here that the dependency is basically the normal order of execution. And then in these F2, F3, F4, F5, I can basically expand them into more things, right? So F2 is a spawn that does something. That something is actually built up of smaller building blocks, T2, T6, and T7 concurrently, T13 and T17, right? And it's just express that with regular code. And the same for the other parts of the graph, right? So this is how you can express simple things in this model, right? Let's try to build a more realistic example. Let's try to have a concurrent quicksort. So you'll have kind of the basic stuff, the basic algorithm. You, under a certain threshold, you use a regular sort, and then you do some partitioning, and then you basically spawn you execute those two things. But this time, you want to do it concurrently. So what you want to do is do a spawn, do the thing on the right, and then on the regular thread, do the thing on the left, right? And at the end, when both are done, you will wait, and then you can move on after both parts are done. Now, the current Hylo language is not yet 1.0, so there's a little bit of ugliness. You have to declare all those things with, how do you see it in, and I don't have any screen. Okay, now it's back. So you have to do a little bit of ugliness in here, but I kind of like to put this in because you can see actually what happens, right? You have pointers and you pass the pointers, so you're not moving anything, and you're doing some copies of the pointers, which are really cheap. So that's everything that you need to know. It's kind of easy to have that mental model of what's going on. Again, the hope is in a future version of Hylo, this would be much nicer expressed, and you don't have to put all this machinery that's low level. But yeah, it's still in progress. Okay, let's do a concurrent inclusive scan. And for those of you who are in Bryce's talk, I'm not going to put his example. What I'm going to put up here is the traditional implementation that's actually in P2300, so the send as a receiver proposal. That's the actual example put in there. Does it look reasonable? Well, once you get the hang of it, it does. Kind of squint in there and you realize what's going on. But it's hard because it's using a different paradigm in here. We're not executing code. We are building code that describes how this could be executed, and you're not even sure if you ever execute that stuff. So if you just look at, if you completely ignore the problem and you just look at how this code lays out, it's like, it's hard. You have a transfer just, you have some partials that you move around and you bulk, then you have those partials again, and then do partials, then why do I have to do all this machinery for something that can be expressed in the code? This is how you would put this into a future version of Hylo. And beware, this is a slide where you have to do a little bit more changes to that. I just took the current example and adapted it. But the basic idea is that you just have things into the code. You express what you want to execute directly in there. And you don't have then functions. You just use semicolon. That was intended for. Hylo doesn't even have a semicolon. But if you look at the structure of this thing, so again, ignoring the problem details, it just looks like normal blocks, right? If you would consider the spawn to be like an if statement, it's kind of the same thing, right? Nothing that's complicated in there. So I hope that kind of makes sense. That gives you an idea that you can build more and more complex stuff with the simple primitives. And that's it. That primitive is spawn. And of course, you also have to wait for it. Let's talk now about structure concurrency. Right? So again, we are talking about the morphe, the form of it. So before that, let's start from structure programming. Structure programming defined back in the day, the 70s, by Dijkstra, Hoare, and Dahl. At least that's... I do refer to the book as the main source of what structure programming is. It has multiple points in there, but two are mostly relevant in here. Is like every operation has one entry and one exit point, and you build everything out of those type of operations, and you are able to recursively decompose your programs into operations like that. Like have a main, you decompose into something else, decompose to something else, and eventually you end up with ifs, with fors, and with everything, right? Everything is built up of these principles. So into code, you see that everything has the same structure, right? You have an input and an output. Everything has the same shape. Even the ifs and the whiles have the same shape. And inside the whiles, you have things that have exactly the same shape, right? So is that conservation of shape, that symmetry of shape, to refer to Victor's talk. But why is it important? Like if you read Dijkstra's paper, the main thing that he argues, besides saying that the human mind is limited, is that this thing helps with local reasoning, right? So it's easier to reason if you have structures that look alike than to have go-tos all over the place. If we translate this to concurrency, it's exactly the same thing. Basically, what we've done is we've created a new type of block between spawn and await that has one entry and one exit point, right? And it just behaves like a function call. You can actually hide this into a function call and everything will look fine. You execute F1, then you execute this block, which may do stuff concurrently, and after both of those F2 and F3 operations are complete, then you execute F4, right? Its structure is really easy to reason about. How would recursive decomposition for concurrency work? Well, you'll have a program, a large program, then you start dividing it. You say you have an initial phase, you have a final phase, and then you have some more phases in between that can run concurrently. And then each of those things, each of those blocks, you can divide it into more blocks and more blocks. And at each point, you can say, I have more and more blocks, and you can go and divide them. And this too helps with local reasoning, because you can look at this part over here, and you know that it has nothing to do with everything else, right? If you have a concurrent bug, if you would have a model that would allow you to have concurrent bugs, then you know you're just looking in here, right? You don't have to look into the entire program. So that local reasoning is just so much easier to work with. And the term that I like to use these days for this is reasonable. We want reasonable concurrency, which means two things in my mind. First, you can reason about it. You can look at the code and see this is what's happening, and I can prove that just by looking at the code. I don't have to execute the code to know what's happening. And then reasonable in the sense of there should be no surprises in there. It's just as expected, right? Not out of the ordinary. And that is the holy grail of writing code. Now, we do need to cover one more aspect of structural concurrency, which is stack access. How would this thing work? So here we have 3 blocks. And we have F1, F2, and F4. Because they're in the same function, they would execute on the same stack, right? That is programming as we know it, imperative programming. But then we have this concurrent relationship that says F1 needs to be executed before F3, and F3 needs to be executed before F4, right? That's by design. That's how we constructed this. We set a spawn, and then F3 needs to execute after everything that is done before that. And because of that await, F3 needs to finish before F4 is executed. Right? No, because I'm trying to say something about F3. Yes. Also, F2 is F2. If we put F2 in there, that's also true. But what I want to say is that while F3 is executing, the stack is still active. That means that F3 can access data, right? So you just seen that I proved that I can have local reasoning on this code. F3 can access data just by looking at this code, and there is no UB in it. This is C++, there's always UB somewhere, but not in this particular code. But in order to do that, you have one restriction, which actually is a good advantage. The future that you're returning from spawn is not movable nor copyable, right? And because you have that restriction, that helps you in local reasoning, as we saw, and then it also helps you in how you're implementing that. In order to make spawn work, you have to have some kind of a spawn frame. And because you know you always have a stack around, you can just put that on the stack. So you can implement this pretty nicely. But there is another type of concurrency, which is still structure, but a little bit weakly structured. And in this case, the future is movable, but still not copyable. And this is an example that illustrates this. I'm having this escaping spawn, right? I'm having a different name for that. And that generates a movable future. That is, I don't have to wait for it on the same stack, right? So spawn work can immediately finish without this being executed. And I don't have that guarantee anymore, right? F3 cannot access data anymore. And again, the spawn frame cannot be put on the stack because the stack may be disappearing, so I need to put it on the heap. So by relaxing a little bit this, we lose some of the benefits. This is a comparison between the two models. So a structure concurrency that has a little bit more structure to it, it can access local stack, it's faster, but it's more constrained. On the other hand, the weakly structure has less structure, cannot access local stack, allocation is required, and it's less constrained, so you can use it in slightly more examples. Okay, so for people who have coffees, please take a sip. For people who don't have coffee, please stretch your arms and your legs, because this is going to be a hard section. Let's try to get focused. This is the key of the entire presentation. If you understand the mechanics of this, like everything, it's easy. So let's start with our example. We want to implement a system that has this constraint, right? That's the concurrency definition. This is the code that implements that. Again, the same pattern all over the place. And this system at design time can be transposed at runtime with something like this, right? I'm having two threads, thread 1 and thread 2, which they are both doing something before this computation is executed. Then thread 1 executes A, then B, then D. Then it goes on executing some continuation. Thread 2 does something previously. At some point after A is completed, it will execute C, and then it will go on and execute the continuation for thread 2, right? Make sense? But this only covers half of the cases. What happens if the time needed to execute C is bigger than the time needed to execute B? Then we have a problem, because if we just map this to our actual threads, this would not satisfy our concurrency constraint, right? So the model would be broken. We can't implement this thing. So this doesn't work, this model. So a lot of naive implementation would solve this problem by adding a blocking weight in there. That's a terrible idea. Please, please try to avoid blocks. They will definitely ruin your performance. So what we want to do is have something like this, but without the blocking, right? What can we do about it? And ironically, the answer is on this slide. There is nothing else that we need to do to make this work. We'll just rearrange a little bit the drawing and do something like this. We can swap around the work, right? We can make thread 2 continue to execute D, and then whatever was there to be executed on thread 1, and then thread 1 just go on and execute everything that's on thread 2. Right? And I know many of you will say, well, but that's impossible. How can we do that? But we actually have that technology for a long time. And an easy answer to that is using stackful coroutines. You can easily change the stacks around. You're just pointer into memory. You can just go and execute other stuff. Nothing prevents you to do that. In my particular implementation, I'm using boost context as a starting point. So maybe a better way to represent this, Felix, you have a question. Mike is over there.
Yeah, I have a question. How do you control which of your code is executed on which core? Because that is what's actually interesting. So the thread is just an abstraction, which is running on the physical core. But the interesting point is, how do you ensure that certain things stay on that core?
That is an excellent question. There are two types of ways of handling that. So first is, you don't care. And most of the time, that is the right answer. You don't quite care on which core you execute. The other thing is you do care, and in that case, you have to partition the work in such a way so that you have some affinity strategy in there. I'm going to briefly talk about that later. Not a lengthy discussion, but briefly. If you think about the typical application with thread pools, right? We don't care, because all threads are created equal, more or less, right? And you just swap things around. You never control which task gets on each thread. And that is the most common case for a lot of the concurrent programs. Not all of them, I agree, but excuse me?
You said that you're using the level 1 cache of the process, of the CPU.
Yes, I'll get back to that. But in here, what you need to realize that in my previous example, everything is in there, right? So you don't quite care which thread it is, because everything is local, right? Yes, I agree with you. There will be a little bit of switching around, but there are also strategies of coping with that as well. So let me go on with this. So I'm trying to draw this slightly different. On the y-axis, I'm drawing my memory, and what I'm particularly interested in about stack access. On the x-axis, there is time, right? At the start of this, I have stacks for thread 1 and thread 2. Those are my allocated blocks of stacks. And I do have something that executes before me, let's say on thread 1. And let's say thread 2 is sleeping, doesn't have anything. It does have a small stack consumption, but it doesn't do anything. We execute A, right? So you see the stack growing, stacks grows down. Stacks growing on for thread 1, thread 2 is still sleeping. At that point, we do a spawn, so we send a message to thread 2 to wake up. Thread 2 wakes up, and the first thing it does, it allocates a stack for a coroutine, right? And then we can execute on that coroutine, and we execute C on that coroutine, right? In the meantime, thread 1 executes B, and B finishes whilst T still did not finish. What do we do here? Here we do the thread hopping thing, and we say, thread 1, the only reasonable thing for you to execute is what's next on thread 2. And then after we finish C, we do a thread hopping again and say the only reasonable thing for you to execute is what's on thread 1, right? And then basically we switch the threads around. And you'll see that thread 2, which is yellow in my case, will execute D, but it will execute it on the stack of thread 1. And thread 1, which is blue, will continue on the stack of thread 2, which probably either goes back to sleep, takes another task from the pool, and all that. Does that kind of make sense? Like an idea how that would work? The one key thing to remember here, we're used to seeing threads and stacks always put together, but they are not, right? It's easier to see things as I'm having a stack that just varies over time, and the thread moves that stack variance over time. And then I'm executing on this stack, or I'm executing on the other stack. It doesn't matter. It's just an instruction pointer that I'm moving around, and I'm executing code on there, right? So we can easily do that. It's just not that common practice to have this. So the key part in here for this thread hopping is that when you start an operation, the start thread and the end thread may be different, right? You may start on one thread and end on a different thread. You can do that for regular operations. You can do that for function calls, like for everything. Once you go down this path, a function does not necessarily end on the same thread that it started. Okay, now let's switch to another aspect, which is also very important. What happens if I'm trying to do a spawn and I don't have enough threads? Right? I'm having, let's say, a thread pool of 10, and then I'm just spawning things. What happens? The right thing to do is to not just block there and wait for threads, but the right thing to do is execute the task inside a wait, right? A wait looks and sees, I do need that task. There's nobody else who can execute it, so I'm going to execute it locally. Let's put it down into the same type of diagram. So I'm having thread A and thread 1 execute A and B, while thread 2 is busy with some other work, right? It does not have the bandwidth to take new tasks. So at that point, we decide like there's no point for us to wait. We don't like waiting. So what we can do is execute C in place and then move on with D and other stuff, right? That's simple mode. That doesn't involve thread hopping. Does it make sense? Good. Now let's drink another sip of coffee because we finished the hard part. So I'm having some early measurements here to see kind of like, is this the right direction or not? And I'm specifically trying to emphasize early here, like early measurements. We are using micro-benchmark and we're just testing prototypes, right? So don't just go and say like, I've seen this measurement and it's way better or way worse or whatever, right? In general, in concurrency, it's hard to find good benchmark, right? Everything is kind of micro-benchmark because it really depends on machines, on the program, on everything. So please always remember that. So the first performance measurements we are going to look at is the Skynet benchmark. The question that we are trying to answer with this benchmark is, does it scale? Can I have a model that just works on big projects? And the idea of this micro benchmark is you create a task which spawns 10 new tasks. Each of them spawns 10 new tasks and then 10 new tasks at each level, right? And then when you reach at the bottom level, you need to have 10 million tasks to be created. The original benchmark was with 1 million, but I just bumped it up because it's better this way. And then at the final level, you don't do anything. You're just returning your order number, and then you just sum it up all the way up. So it's a really strange thing. You're actually creating 5 quadrillion, 5 trillion tasks in this benchmark to do nothing, right? Just summing up some numbers. So let's look at some performance measurements. I'll start with the Go implementation to set up the stage. That's what the author did. And for this particular thing, on this particular machine, it ran in 2.4 seconds, the median time. If I have this implemented with my concur to full library, that executes in 1.3 seconds, 1.9 seconds, and 1.7 seconds. Well, I'm having 3 numbers here because I've implemented three types of the model, the benchmark in three different ways. First is with structure concurrency, right? So I explicitly do a spawn and a wait for each of those 10 tasks. Then I'm having a weekly structure thing. And then I have this called bulk spawn, which I haven't shown you, which is like I have a dynamic number, please spawn that many tasks for us. It's like more like a concurrent for. And for structure concurrency, you don't need to have an allocation per frame. So the frame is local. So it performs better than the weekly structure model. And you can see that. And for the weekly structure model, you have to do 10 allocations, 1 for each task. For the bulk spawn, you only have to allocate 1 time the frame, and that's why you would get better number than weekly structured. So I think the answer to the question so far is yes. To be fair, I also implemented this in Hylo, and not that great, but still good, right? Please consider that Hylo did not reach version 1.0 and did not quite go into optimization, right? So those numbers look pretty good to me, especially the structured concurrency ones. There's some work for us to do. We need to see why that's slower. And of course, there's some bug somewhere, like always. But then, of course, I need to compare this to C++. And I'm having for C++ 3 distinct implementations. The first one is just with coroutines. I'm using the task type from stdexec library. And note that I don't have any concurrency in here. It's just coroutine work. I don't quite need concurrency for this type of problem because the cost of spawning is the thing that I'm measuring. So you see it's a little bit slower than concurrent to full. The fastest thing here is the concurrent version, which are having the standards receivers implementation, plus that task type, still using coroutines, because I need type erasure. And that's the fastest implementation here. That's 20% faster than the structure concurrency in here. So being 20% slower than the fastest implementation that you can get, it's a good number for an early measurement. The thing that I want to point out is I also try to implement this with sync weight, which also comes from the P2300 senders receivers, and that just doesn't work. It deadlocks. The moment you have more sync weights than your actual number of cores, you're going to deadlock, right? So that's really nice because this model doesn't have any deadlocks and you can't make it to deadlock. Right, so the interpretation for this early benchmark is can handle large amount of tasks in parallel. That's what we wanted to check. We don't have any deadlocks, so that's a good sign. We have good overall performance, right? So our first implementation just was pretty fast, but it's slower than sender receiver. 20%, I would see that as a good sign. Okay, another benchmark to test the speed up, and that is like, okay, we've seen this performance, but this benchmark doesn't quite make sense because nobody's going to do that in the real world, like extremely biased. So for this one, I tried to compute the Mandelbrot for a 4K picture with a depth of 1000. Didn't do the graphics, but just the core part of it. And I'm bulk spawning for the rows, right? So I'm just having each rows done independently. And of course, if you know the problem, you have some rows that are heavier than others, right? And it's a little bit a more realistic thing in which you have tasks with different nodes. And by the way, I'm only talking about CPU here. I'm not talking about GPUs at this point. And this is the median duration time. With the more cores we add to the thing, the better. It's still running on my machine. But this graph you can't properly see anything. So this is a better graph which measures the speed up versus the ideal speed up, right? So that's linear. And in here you see the blue one, which is the thing that we've measured, is pretty close to the ideal. So I do have, I think, 12 cores on this machine. So you see that the performance stops at 12, right? Victor, you have a question?
I saw the number 16 there, so immediately I have to ask, have you benchmarked beyond 16 cores? Because 16 cores seems like an Etch-a-Sketch now. Like we have many more cores in machines.
Oh, on this machine I only have 12, so
okay.
I can, like, but it's going to be a flat line, or maybe at some point it will decrease.
Okay, thank you.
I've tried that multiple times, and usually it starts decreasing the speed up. I think you can see it in here. Yes, you can see it in here. So with 15 cores, it's 10.4 the speed up, but with 16 it's 10.47 and 10.41, right? So after a certain point, if you have more work than the actual number of threads, you will just having worse and worse performance, right? But that's the limit of my machine. And again, it's a laptop, it's like not a big thing, right? Like, of course, you have to imagine this for longer machine. And it has cores of 2 different types. So you can see that over here. So around 8 cores kind of changes a little bit the shape. Not all the cores are as efficient. But up until here, the results are pretty good. If you ever seen these numbers, if you ever saw those types of graphs, those results are pretty good. So up at 8 cores, I have something like 95% of the ideal speed up. So that's usually very, very good. Does it make sense? Good. Now we get into the complicated weeds of trying to analyze what we've built. And again, this one, we're going to cover a lot of ground with this section. So, by the way, you do realize that by now I do presented concurrency model, right? I haven't presented too much code, but I did present the concurrency model, which can be used to implement a lot of things, right? It's so simple that I cannot invent a million slides with it, but it is a concurrency model that works. So in this section, we're trying to analyze how well that works on different from different perspectives. So, first one is modeling concurrency. So we can express simple constraints, and that's most of what we need. Like I would say that we follow the Pareto's rules. 80% of what we need is with the simplest rules. And then, of course, you can always go to the most complex stuff for the extra 20%. So in here, we're pretty good. The model offers us a forward progress guarantee. Once the task is started, it will be executed. There's nothing blocking it, waiting for other things. And because of that, eventually all the tasks in your system will be executed, right? And by the way, I say task here, but please do not imagine dynamic things. Like tasks are code structures, like the branches of your if clause, right? That is a task for this model. What we haven't implemented yet is conditional concurrency, right? Sometimes it's concurrent execution, sometimes is mutual execution, and doing it over distributed tasks. That is still not implemented in the model. You can do it by hand. You can always do it by hand, trying to do manual bookkeeping. So on modeling concurrency, we're doing pretty good. Safety. Victor?
Before you move on from the model, how do you handle cancellation, task cancellation in the system?
I do have a slide on cancellation.
Excellent, thanks.
Unfortunately, not necessarily where I would like it to be, but yes. Safety. There are no race conditions with this, right? We directly express the relationship in there. Remember, the model is inspired by Hylo, where there's no undefined behavior. You can't have two people writing it, or if somebody is writing, nobody else can read it. So by design, the model doesn't have race conditions. Now, if you implement this in C++, of course, you have to deal with the race conditions that come from C++. But the model itself doesn't have any race condition. If you follow the way of working of the model, you don't have any race conditions. You don't need additional synchronization, right? We've expressed concurrency using these constraints, so why would you ever do additional synchronization? We talked about for progress guarantee, we don't have any deadlock, right? We're not waiting on anybody else, no deadlocks. So on safety, big thumbs up. I think the model is pretty good. Performance. No blocking waits, as we discussed, that's a good thing. Spawn and away synchronization, we've seen is not ideal, but it's acceptable. Like this 20% slower than what we currently have as the golden standards, the send as the receiver model. So I think 20% compared to that is pretty good. Also, please note that the number of spawn and awaits in the code, if you're designing this with performance in mind, it should be relatively small, right? Because each time you do a spawn, you're expecting to move work from one thread to another. And that's a huge impact on performance, right? As soon as you start moving stuff from your code, from your core to another core, that's, I forgot how many orders of magnitude, 2 orders of magnitude slower, something like that. So there should be a relatively small amount of spawns and await in the code. The cost of a spawn. So at this point, the technique that I'm using is doing a memory allocation for the coroutine. So that may be a cost, but that's easily optimizable because you can reuse the same stacks. I'm using the callcc primitive that's coming from Boost context, and they have benchmark in there that's pretty fast. I forgot, something like 3 times slower than a function call, very, very fast. And then there's some synchronization for spawn. It's just like you put a task into a thread pool, so that amount of synchronization, you have it in there, plus another atomic store. The cost of a weight is a little bit bigger. So that 20%, I don't have good measurements, but I suspect it comes from a weight. So I do need to have a small memory allocation in here that can be optimized, but currently I do have that. I still need to have a call CC call in here. That's also fast. But the synchronization at this point is a little bit harder. And I'm doing two types of things in here. So because of that thing, if I don't have enough cores available, I'll do it on the I'll do it in place. I do need to extract the task from that thread pool and put it in there. So that's an extra thing that the sender and receiver model doesn't do. And then there is this edge case that I cannot continue on the continuation unless the other thread has given me the continuation. So if the thread pool started to go on that path of executing that task, I need to wait for it until it gives me a continuation. So I'm having a blocking weight in there, which is typically very, very small. But if you're only doing that, it will show up in your benchmark. Again, 20% for this type of thing, really good. But it's a cost. We need to be aware of that. There are some optimization opportunities in here. So I haven't implemented that, but we can reuse coroutine stacks. It's pretty easy to reuse them. Actually, we can know how many we have, so that's really good. We can have local stacks, so that would improve locality. So that's coming back to your point. You don't need to go to someplace else. You can have still things locally, right? So then even if you're moving stuff around, it's still kind of closer. I get your point, and it's still not the same thing, but it's still getting a little bit closer. And then that 20%, that really bugs me. I would hope there is some way of optimizing it. I had a couple of ideas, but after I traced them down, they were both not good. But yeah, keep hoping. So on the performance side, I would say like, yeah, it's good. It's not the best, but it's good. Again, early prototype. The stack usage size. Now, I bet a lot of you would ask, what about stack usage? You're using stackful coroutines. That will eat all my stack, all my memory, and it will go to my neighbor's house and borrow some memory from there. And the entire neighborhood, it will just borrow memory, especially for that Skynet benchmark, right? No? First, let's start with the basics. For the worker thread, the amount of stack that we really need is really small, because the only thing that we do on the worker thread is just jump to a coroutine. Right? We don't execute stuff in there, so we really need a small amount of stack in there. And now the biggest thing, and I was extremely surprised when I found out this, when I just found it by running the model. You can't have too many coroutine stacks because of the way we've implemented this, which is you only create a coroutine inside of the spawned work, right? So it's not the first person who enters the spawn that creates a coroutine, but it's the other thread that creates the coroutine, right? So if you only have 10 worker threads, then you can only have 10 coroutine stacks, right? So the number of coroutine stack is directly proportional, is kind of similar to the number of worker threads. In my model, I'm also having a stack for a weight that's easily optimizable, but in general, you get the idea, right? So it's bounded. So the stack consumption from there is kind of the stack consumption for every application that has a thread pool. It's kind of the same thing. As I mentioned, we do have a small stack for a weight. This is really, really small, just to be able to get a continuation from the await point. And that can be easily optimized away. I can always put that on the stack. But currently, I don't have that. So the bottom line is that this model requires a low amount of stack. It's comparable to an implementation with just threads. Actually, I bet it will be, like if you optimize this, it will be smaller than a most of the applications that use threads, because in the application that use threads, you have blocking, then you keep increasing the number of threads that you need. Here, we only allocate the number of threads that we actually need, so we keep that bounded. But there are some optimization opportunities I mentioned. Pre-allocate the stacks, reuse the stack, and local stacks. I think this using local stack will actually optimize a lot of the application. So on stack usage, to my surprise, that's a big win. Now, not everything is that green. Interoperability. First, you can't properly use thread local storage anymore. I mean, you can, but you have no idea on which thread you're ending up with. So, but don't use it anyway. That's a bad practice. Like, if you know what you're doing, like, yes, but you should be an expert to use thread local storage. But there's a bigger problem. If you have external functions that are calling into your code, then you don't know what they expect, right? And probably they would expect you to return on the same thread. Otherwise, they may stop working. You don't know that, right? Because you can't control that thing. So in that case, you may be forced to pessimize that, to put a blocking weight to make sure that you're returning on the same thread. And one example that I have here that I bump into it is if you create a std thread, you execute something and then you do the thread hopping. When you end that, you have to make sure that you're on the same thread. Otherwise, it won't work. Right? Because otherwise, you're destroying the stack of somebody else's thread. So you always have to have that thing. So this interoperability thing is a thing. It's up to the application how big the problem is. If it's just at the end of the program, like it's a really small cost. But if somebody else calls you for each little thing and you have to do a blocking weight, then that's probably a big cost. There are some optimization opportunities here. You may have affinities for scheduling. So you may say, I have a thread pool of 10 tasks, but let's try to have some affinity so that I'm trying to get back as much as possible on my original thread. That again comes to your point, Felix. Depending on the problem, you can address it. But yes, it's a little bit more work for it. It's not supported. It's definitely not supported by the model I'm having, and depending on how it turned up, it may be directly supported in the model or maybe remain for manual work. So on the interoperability side, not that great, unfortunately. I mean, you have to have some kind of negatives when you keep saying a lot of positive side, right? It's a balancing act. Some missing features. We also need to discuss about those, right? Copyable feature. So far, I've only talked about movable features, but none of the features I had was actually copyable. This is one point that Sean Parham was keep pushing me, like, you have to copy those things. Like, yes, I know, Sean, but I'm still not there yet. The thing is not that trivial, right? So if you have the regular features, then you have two input threads, thread 1 and thread 2. And after a wait, you still have two threads, right? Maybe in different order, but you still have the same threads. If you start copying the future, then suddenly an operation that previously used 2 threads will now have, I don't know, 20 threads, right? So there's a little bit more involved synchronization logic to be handled in there. And the second point that Sean kept pushing me is cancellation. And yes, this is a larger topic, but we do have a good story for it. There are typically 2 types of cancellation when the car doesn't need the result anymore, right? So either instead of calling await, it calls cancel or simply drops the future, as the model that Sean wants. that we need to propagate a signal to the work saying like, you're not needed anymore, please finish up as soon as possible. It's still going to be a cooperative cancellation. But the other case is when the work is cancelled somewhere from within and it cannot produce a result, and then it has to notify the caller about the impossibility of delivering results. So those are the two main things. At this point, I'm not seeing any big problems in there. It's just a little bit of work to make that happen. Another important thing that we need to have is conditional execution. That is, don't make spawn immediately start new work, put some conditions in there, and based on that condition, sometimes spawn it, sometimes defer it. So there's a little bit more involved in there. One example is, and I do see that occur a lot in practice, but we still don't have a good paper for the C++ standard committee. It's something like a serializer. Right? You can have n tasks from different parts of the application, but only one can run in parallel. Right? You can't have two of those execute at the same time. Imagine a game that wants to save some state, right? And that save is triggered by a different thing, like the player dies, some other player is spawned up, or something's changed in the game, right? And you have different triggers. You don't want all parts of the application to just save immediately. You want to serialize those things. So that is an important feature that somehow needs to be implemented. And then, of course, and that's a big chunk of work, other execution contexts like I/O, timers, GPUs, custom execution contexts. Like, if we never get that affinity thing into the model, then at least what we need to do is provide you the ability to customize that and say, okay, I'm spawning this, but you're customized on running this on whatever threads or however you want to run things. And then, of course, algorithms, a lot of algorithms. And for that, again, we need to use the Aristotelian discovery process. We just have to look in the wild and see how all those things are being done, see all these examples that we have there, and see what are the useful algorithms that we need to have in the library. We know a couple of them, like, for example, waiting on multiple futures, waiting on the first future, whatever, but I suspect there will be many, many more. Okay, so some takeaways from this. We've tried to approach concurrency from a holistic approach. We try to look at it from a theory point of view. We try to look from the form and the substance of it, kind of have this different perspective on it and try to align the stars so that we have a simple model. From a theory perspective, we said that concurrency is about expressing constraints, right? Concurrency is not about mutexes, it's not about threads, it's not about anything. It's about expressing constraints, right? What would be the limits of the task to be executed? I think that if we all started thinking in terms of, in those terms, life would be much, much easier. Why? Because there are only 3 possibilities at runtime, and most of the time there are just a couple of constraints, 4 of them, from which one you can easily cross off at design time, right? So if we write our software just with these things, concurrency would be much better. From the form perspective, we have a model that can easily express concurrency by using this pair, spawn and await, which is kind of like a regular operation, like an if block or a while block, and doesn't require you to write thing in a different style. You'll still write the same type of imperative flow with structures and all that. You just have a different a different block to put in there, right? One of the key points that led me to this effort was that Dimi and Dave pushed me like, we don't want to have function coloring in Hylo. I was like, yeah, but send us a receiver, it's a great model. Yes, but we don't have function coloring. Like, okay, so we need to figure out a way to make that happen. If you're using this model, the users don't need to have additional synchronization, right? Everything should work out of those synchronization primitives. And with that, we get structure concurrency, right? Everything looks the same, everything has a structure. So structure concurrency really brings us to local reasoning, which brings us to my idea of reasonable concurrency, right? You can look at something and you can reason about it. You can prove things about just looking at the code without actually running it. And you're just looking at it and say, yeah, no surprises here. I know what it does. It's easy. On the substance side, we see that there are no race condition, no deadlocks. So it's a pretty safe model. We don't have blocking of threads. We don't have oversubscription. We haven't properly discussed this in here, but in general, the model works as it has an internal thread pool, which is bound to the number of cores that you have, and you don't have oversubscription to that, right? If you run out of threads, you just do things in place. The performance scales with the number of threads, and overall is pretty fast. Like, it's not the fastest, but it's pretty good. So we looked at these three perspectives, and we try to put it into something that I would hope I convince you that it brings us reasonable concurrency. You can reason about the code. It's easy to understand, and you can doesn't surprise you, and you know what's happening. That means that we've properly aligned the hyle and the morphe for concurrency into a model that's easy to use, that's entirely safe, that's easy to reason about, and it's a pretty efficient model. So overall, I would say it's a good model. And I would bet that if Aristotle would live today, it would give us a thumb up for this model, like definitely in his spirit. Thank you very much.